Again, so I think I should preface this by saying it's not the set of real numbers that bugs me. It's simply calling them real. And furthermore, that word imaginary for some of those other numbers. It's not accurate and it's definitely not helpful. For starters, the real number set is not even the only way to complete, i.e. fill in the gaps in the number line, the rationals. I'm going to link a video in the description from Veritasium, which goes into something called p-adic numbers. And the reason this is a thing, briefly, is remember how I keep talking about taking things for granted? Well, there was one thing that I still allowed us to take for granted in the last video. Remember, so when I kept saying, as things get closer and stay closer to, I didn't actually define the word close. In other words, I did not define distance. And that's an actual thing. You have to define distance. Using the intuitive notion of distance, you get the real number line. Using different notions, you get something else. So that's one. It's not even the only way to do it. And, and I'll leave that bit of it at that for now. The other reason, and this is more directly as to the whole question of realness, is that in a very in a technical sense, exactly 100% of the real number line consists of numbers that are not physical or even necessarily describable. Yeah, and I did say 100%. And this is something I'm going to obviously have to explain a little bit. Now, to explain this, first we need to talk about infinities. And yes, that was infinities, plural. Okay, so anyway, so let's start with the usual notion of infinity, and that is the natural numbers. And we say that the natural numbers are countable, which means we can count them off. 1, 2, 3, and eventually, no matter how big of a whole number you can think of, eventually we will get to that number. We just have to count high enough. And the thing is, a lot of the number sets that we typically deal with are also countable or countably infinite. The same kind of infinity as, implied by the natural numbers. Let's take the integers. Pretty much the same deal, except when we count off, we can count off like 0, and then we can count off positive, negative, etc., and so forth. And we will eventually hit any integer you can think of. And even the rational numbers, which involve two integers. It takes two integers to describe a rational number, and yet they're still only countably infinite. And here's just an example of how you can list them all off. So instead of just, positive negative pairs, we have, well, so we have the positive negative pair for 1. Once we get to 2, well, we have positive negative as well as the reciprocal and positive and negative. So here's a group of 4. And for thirds, well, we have two groups of 4, one for 3 and 1/3, and one for 3/2 and 2/3. And if we keep on going like this with the fourths, skipping 2/4 because we already have that, fifths, sixths, sevenths, etc. We just keep one upping the denominator and doing this, grouping by 4s, and we will get every single rational number. So yeah, that's one way to do it. So what does it take to have an infinite set that you can't count off, that you can't just make a list of? And Well, that's actually so let's start with some things that won't make it a greater infinity. Having larger sets of I mean, you can have a 10-dimensional set of coordinates, 10 numbers required to describe it, 10 integers, and it still won't be a different infinity. Similar, you could have 10 rational numbers, so 10 fractions in a row to define your coordinates, and it still won't be a greater level of infinity. You can't just multiply infinity by a finite number and get something else. Infinities don't quite behave that way. So, let's cut to the chase a bit and talk about why the real numbers aren't countable. So, suppose we have a real number, some number on the real number line. And unlike, say, the square root of 2 that we can define as the diagonal of a right triangle with sides length 1, so we can describe it. We can also describe it as the root of the polynomial equation x squared minus 2 equals 0, or more specifically as the positive root. We can define pi or tau in terms of the ratio of a circle's circumference to its radius or diameter, but in the other order. And there are all sorts of other numbers that we can describe. We can give a recipe for these numbers, either with a physical construction, or like with the triangle, or by some other description, as with the circle. So there are a lot of numbers that we can describe. Trouble is, even these are only countably infinite. Whereas, suppose we have a real number that isn't one of these. It's not one of these numbers that we have a recipe for. It's not a number that we that we can draw using only basic tools like straight edge, compass. It's not a nice ratio involved in some shape or other. It's just one of those sequences, one of those convergent sequences, or from the last video, or rather one of those infinitely many convergent sequences that all go to the same place. And that's the only way, we can represent it. Effectively, you'd need all infinitely many terms in the sequence to describe it. So that's not the technical reason we run into problems, but I hope it gives you a sense of just how much weirder some numbers can be than other numbers. Now, to actually demonstrate that there are an uncountable number of real numbers, which we've already established is not an easy thing to create. I mean, like a lot of different large number sets that seem like they are larger than that contain the natural numbers are still listable. We can count them off. We can list them. It doesn't break the basic infinity. Hmm, those two words together do sound a little weird, don't they? And yet I'm saying that the real numbers as a whole do. So the best way to show that they can't be listed is to try and list them. And I'm going to use something called a proof by contradiction. And this particular proof is a classic one known as Cantor's diagonalization argument. And Cantor is known was he was very good at really messing with your head when it came to anything involving infinities. All right. So before I get to the proof, though, I just want to set things up so the proof itself is a little bit cleaner. And so first of all, just a reminder of what it means to have a decimal expansion. It means, suppose we're somewhere between 0 and 1. Now, when we say that the expansion starts with 0.2, that means we're in the 0, first, second one of these intervals. And so they're, you again, so rather you break the line segment between 0 and 1 into 10 pieces, and one of these pieces corresponds to starting with 0.2. Now, when you take the next decimal place, you are doing this again to here. So you're zooming into this interval and you're cutting it into 10 pieces. And the next number will determine which of those pieces you end up in. Now, a slightly cleaner way to do this is, is using binary. So here I've drawn out an equivalent picture in base 2. Now, in base 2, if you put it, all we're doing, instead of dividing into 10 pieces, we're dividing into 2. So here's the middle of the interval, here's left, here's right. Choosing a 0 means you go left. Choosing a 1 means you go right. So say we pick 0, we go left. Now for the second digit, or bit, which is just binary digit, so for the next bit, we, again, 0's left, 1's right. Suppose we choose 1 this time. So now we divide by half again. And if we choose 0, we end up in this left bit. And if we choose 1, we end up in this half of the interval. And we can keep dividing by 2 over and over and over again. And either we just keep on going forever with no particular pattern, or we, enter a bit of a loop, which gives us a that would give us a rational number. And or we can terminate by saying at a certain point, just say, now always go left. That means from here on, all zeros. So that's another way to say, terminate the expansion. Or we could do all ones. That was like, remember the point ones is 1? So we could just say always go right. So always go left or always go right. Either way is effectively done. So the next bit is actually attempting to make a list of all the real numbers, or just to make it a little simpler, all of the irrational numbers between 0 and 1. All right. So suppose we could list out all of the the real numbers between 0 and 1, or all of the irrational. And it would look something like this. So this again is base 2, so all of these are just going to be ones and zeros. Now, so again, suppose we could list them out. All we have to do now to show that it's not possible to do so is, for an arbitrary list, we would have to just find a number that's not on the list. And for this list, well, here's what we do. The reason it's called the diagonalization argument, by the way. So here's a number. All right, here it is. So this one has a 1 in the first place. I'm going to make this one a 0. This one has a 1 in the second place. I'm going to make that a 0. This one has a 1 in the third, also a 0. This one has a 0. That one I'm going to make a 1. So in other words, what we can do is we can create a number that disagrees with each of the numbers on the list in one place. And since it disagrees with every number in at least one bit, we know it's not on the list. And there was nothing special about these numbers. I could have done that with any list of numbers. It's just whatever you have here, flip it. Whatever you have here, flip it. So just go along the diagonal and flip everything. And that will guarantee a number that's not on the list. And there we have it. There is no list that contains all of the real numbers, even just between 0 and 1, much less, negative infinity to infinity. So yeah, it's a whole other infinity. And expressing in binary also gives a little hint as to what it took to to actually break that infinity in the first place. So another thing we can do with a given string of ones and zeros is we can assign each of them to one of the natural numbers. So we have a 1 in the ones place, a 0 in the twos place, and so forth. And from these, we can create a set that includes 1, doesn't include 2 or 3, includes 4, includes 5, does not include 6, includes 7, and so forth. Now, every single binary expansion between 0 and 1 can be, associated with one of these. And what that means is the set of binary expansions of the numbers between 0 and 1 corresponds to the set of all sets of numbers. So every one of those corresponds to some subset of the natural numbers. Again, inclusion determined by whether the bit's a 1. So every such expansion corresponds to a subset of the natural numbers. And all the expansions correspond to all possible subsets of the natural numbers. And yet, and another way we can think of this in terms of the, you know, arithmetic on affinities is we have two choices here, 1 or 0, two choices here, two choices here, two choices here, two choices here. At everything, we have two choices. So there are basically 2 to the infinity choices. Now let's clean that up. 2 to the infinity of these things. So remember how I said just multiplying infinity by a finite number was not enough to do it? Well, it turns out taking 2 to the infinity is. Um, and it should probably mention at this point, we don't actually just use the infinity because there's more than one. We have, um, it looks more like this. So for some reason, we use Hebrew letters, alephs, for infinities. The first one we call aleph naught. The second one, aleph 1, which we can also write, which is also called C, which is short for continuum. So yeah, so if you take the set of all subsets, which is called the power set of an infinite set, you will one up the infinity. So that's what it takes. You have to take the set of all subsets. And yeah, so that's essentially what the real numbers end up being. They end up being the same size, technical word cardinality, but they end up being the same size in this sense as the set of all subsets of the natural numbers. So that's what it took to break that particular infinity. So one consequence of this is that all of the numbers we know, rational numbers, radicals, etc., all of them put together are still utterly dwarfed by the set of all real numbers. And we can actually demonstrate this with the rational numbers as follows. Okay, so what I have here is I've drawn the real number line, and I've, labeled, some of the numbers on there. And I've started this off, and I'm going to tell you what this is about. So, as you may recall, I showed a way to list all rational numbers one at a time. So what that means is I can, go along that list, starting with, say, 0, 1, -1, and then moving on to the halves and twos. And I can start by wrapping 0, the first one, in an interval of width 1. I can wrap the second one in an interval of width 1/2. I can wrap the third one in an interval with 1/4, and I can keep on going just all the way down the list. So what I have is like so what we'll have if we do all of them is every single rational number will be wrapped inside an interval half as big as the previous one. And the grand total of all of these is as follows, well, which we've already seen. Well, or rather, everything from here on is equal to 1, so this whole thing is just equal to 2. So this corresponded to the in binary, if you'll recall. So the whole thing adds up to 2, which is a finite number. So that's already something right there, that we've contained the entire set of rational numbers in a finite, width, effectively. But we can go a step farther. See, there was no rule that said that the first interval had to be length 1. In fact, we can make the first interval as small as we want. So let's say instead of length 1, it had been some length that we call epsilon, which is just some positive number. This is our default stand-in for a small positive number in math. And the next one then would be just epsilon over 2, and this one would be epsilon over 4. So instead of ending up at 2, the entire sum would be 2 epsilon. And epsilon, again, is just a positive number. We can take as small a number as we want. And then we can go even smaller than that. If what that means is we can let epsilon go at its positive, but we can let it get as close to 0 as we like. And since we can wrap the entire set of rational numbers in a set that, the grand total of which has a width as close to 0 as we like, well, the width has to be 0. Just to recap what that means, the 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 width, the substance of the entire set of rational numbers is nothing. In the real number line, it's just dust. It's just a bunch of dust that you can collapse to a point. That's the rational numbers on the real number line. And the real numbers, the irrational numbers are everything else. The entire substance of the real number line is in the irrational numbers. And even if we start throwing in like, you know, things we know like pi and root 2 and pretty much any number we can describe, any number that can be described as a root of a polynomial, well, it turns out those are also countable. So they're like pretty much everything that we can think of, and more importantly, everything that we will ever actually encounter is is nothing, is none of the substance of the real number line. Furthermore, just to drive home what a strange place we've entered, suppose you want to like actually measure a thing. Now, when you measure it, your measuring device has some precision to which you can measure, which means you can measure to a certain number of decimal places and no more. In other words, your measurement always stops, which makes it a rational number. So any real measurement of anything is going to be a rational number. So we have that all real measurements are rational, and all rational numbers make up none, effectively, of the substance of the real numbers. So finally, we're in a position to ask the question, are real numbers real? And I'm going to go ahead and just say, no, they're not. They're almost real. Rational numbers are real. A lot of our constructible number, any constructible number, we can definitely think of as real. And we can extend our concept of something that can be physical very, very far. But this breaks it. I mean, having all potential physical measurements add up to zero of the substance of the real numbers tells you, well, the conclusion is that like 100% of the real number line is literally just the filler that we threw in there so that we didn't have to deal with some of the nuisances that, well, all of the nuisances that come up when you're just trying to do everything with rational numbers. Okay, so just, short version, the real numbers are very, very useful. They allow us to do things without having to worry about whether we're allowed to do them. All those things that we want to extend from the rational numbers, we do. That's what the real numbers allow us to do. They also allow us to talk about things like limits in a way that is helpful. But 100% of real numbers are utterly non-physical. So the next question, I've made a claim that 100% of real numbers are not real, but the next question, and perhaps this is more important, is, does it matter? Now, considering that we constantly use real numbers when we're modeling almost anything, and considering that it would be very difficult to do so without the real number line being all nice and filled in, I think we might have to agree that it doesn't matter. And that brings me to the whole concept then of imaginary numbers. I mean, if real numbers don't have to be real, then what does it even mean for a number to be imaginary? So, and in fact, if we follow the same standard as I just applied to the real number line, which we need a new name for, but if we apply the same standard, then all a number needs to be a real number, not necessarily real, but a real number, is that it has some utility. That's it. It just needs some utility. So at this point, that puts us in a position to think about the next steps, in particular, numbers that exist in, say, 2 dimensions. And that'll be the next episode. Thanks for watching. Bye.